I'm Matt Needham, and this is my lecture on commercial and industrial air conditioning control systems. Let's look at our first PowerPoint slide here about this air conditioning presentation. Really, when we talk about commercial and industrial air conditioning, we're talking about larger systems for very big buildings, and you're not going to have any equipment this big unless it's on a house that was on the show Cribs or old-time Lifetimes of the Rich and Famous, big mansions. You're not going to have three-phase power or anything else like that, or these big systems that are 30, 50, 500 tons. But we're going to learn a little bit about that here with the commercial industrial air conditioning lecture. And again, with air conditioning, the thing we're mainly concerned about is controlling the temperature. Of course, we want to control the rate of airflow, or the CFM, the feet per minute, the humidity, and all of these things. But we always start with the temperature. Okay. A lot of similarities between residential air conditioning and commercial air conditioning. Obviously, you have to have the refrigeration cycle and motors like condenser fans and evaporator fans or air handler fans and so forth, and compressors. But it's different when we get into bigger equipment. There's more controls, there's much bigger, more expensive motors, and so therefore we do things like more protection for those motors, more overload protection, and there's a lot of planning that goes involved in these big buildings, whether it's for a grocery store or a shopping mall or a high-rise building or a school or a sports venue or a giant condominium or whatever it might be. There's a lot of initial planning that goes involved because there's a lot of opportunity to save energy on this large scale using economy of scale. Okay. Here's a picture of a condensing unit, or maybe I can just look at it and guess that maybe it's a 15-ton condensing unit. So you generally wouldn't see like something like that for an individual home. So it's a commercial application. So we have things like commercial package units and condensing units and remote condensers that we're going to talk about that we use in commercial and industrial. And some of this equipment, I think the biggest centrifugal compressor that's mass manufactured occasionally is the 5,000-ton centrifugal, but we have a lot of equipment above 5 tons to 100 tons that are, commercial industrial equipment for medium-sized businesses. Now, package units is, again, what it says, everything is in one package. Remember, a condensing unit from our last slide, it's the compressor and the condenser in one unit, and then usually the evaporator, metering device, and air handler in a separate unit. But with a package unit, that's all brought together in one giant box. And they use these quite extensively on large commercial buildings. I used to work on a lot of 60 to 90 ton package units, and they just put them right up on the roof, either with a giant crane or in some cases with a helicopter, and they blow the air down from the roof into the buildings. And they have different sections of these really big package units that might be 8 feet high and 8 feet wide and 25 feet long, and they have different sections in there. Also, again, with commercial and industrial equipment, sometimes it doesn't make sense to have individual units for every little room, where we have refrigerant piping all over the place, or individual furnaces for every zone or floor. It makes more sense to have a central plant where we make chilled water and we pump it all over the building, the high-rise, the school, the facility, and we also make hot water with hot water boilers, and we pump that around, and we have these hot and chilled water systems flowing through hot and chilled water coils, and then we can blow air over those coils to provide heating or cooling. And again, one of my pet peeves is a lot of times when we say a hot water boiler, Yes, when we heat water up to 190 degrees and pump it around, that's considered a hot water boiler, even though nothing's actually boiling. So we also do have boilers that make steam, that have steam stations that then heat water or generate power. I used to work on those also. And then with our water chillers, again, probably the most common is a centrifugal chiller. And nowadays we usually have these like 150 tons, again, commonly 3,000 tons of cooling, and we have all of this in one location. Then we're just pumping chilled water around. We have less refrigerant that can leak out and harm the environment, less refrigerant leaks. It's safer, and you have all the equipment in one location that can be maintained. And again, the boilers are going to be in one central location. Then we control these temperatures. Generally, we'll see how chillers supply, on average, about 45-degree water. And then hot water boilers, a lot of times they supply up to 190-degree water, and we send those out to our hot water coils. Again, this can be much higher than what this number indicates here for commercial industrial controls. We have, like I mentioned, very large equipment. And again, though, this makes a good point here about capacity control. We're always going to have some type of capacity control, and as time goes on, we have more and more capacity control with the compressors, with the condensers and the evaporators, the airflow. We have things like variable frequency drive, ECM motors, very efficient, that can ramp up, speed up and speed down, and lower their speed to control the capacity of all these electrical loads. We also have on centrifugal chillers, older ones, vanes that open and close, things of this nature. Also, sometimes we'll have multiple compressors, and maybe on some of the, I used to work on a lot on these 60-ton package units, and if you just need a little bit of cooling, they'd have within this package unit really two separate 30-ton systems, each having their own compressor. It looked like one condenser, it looked like one evaporator, but really it was two separate refrigerant circuits together, and one 30-ton system would run when you need a little bit of cooling and when you need a lot of cooling. Both of them would run. So in a sense, that was capacity control, that you were going to maintain a more stable temperature by not cooling it and having it shut off and then warm way up and then turn the system back on. When you just need a little bit of cooling, you're providing a little bit of cooling, and then when you need a lot of cooling, both compressors would run. So there's various ways that we obtain capacity control. Now, we don't really use part winding start anymore. You can disregard that. That's really not part of real modern 2020 type of air conditioning anymore. And then we've gotten very advanced digital controls, which we're going to talk about for water chillers, to control the circuitry. We want to do certain things like make sure that we have the chilled water pump running before we start the compressor to make chilled water, so we don't freeze up the chiller barrel. And we have a lot of safeties, not just high pressure and low pressure cutouts, but freeze stats and things of this nature. Sophisticated magnetic overloads that are very much quicker reacting than thermal overloads to protect our compressors. So more and more we have this advanced circuitry and a lot of communication to a central plant, to a computer that monitors everything and makes it easy to look at your problems and set your set points and set your schedules. Okay. Now, generally we talk about air handlers, an air handler being like a separate component that is the air that we blow over maybe the hot and the chilled water coils in a commercial industrial application. And this is the thing that really needs to operate the most, because especially in a commercial industrial building, whenever people are there and you're occupied, which quite often is more than what you'd think in these facilities, especially with people working and doing repairs and cleaning the buildings and whatnot. You need to have ventilation. So the blower has to be on all the time. Now, the cooling may not be on, the heating may not be on. Maybe they do a night setback temperature where they don't provide as much cooling, or they only cool down to 82 or 84 degrees at night, or maybe they only heat up to 60 degrees or something like that when the building isn't primarily occupied. But you're going to have fans running quite a bit whenever the thought that people are there, because you need the ventilation, you need to bring in some fresh air, and for health and safety. Also, on larger systems here with the condenser fan motor, you know, you think about little residential equipment, 5-ton equipment, one condenser fan. On air-cooled equipment with commercial applications, for some of these air-cooled chillers or 100-ton package units, you might have upwards of 12 condenser fans, and maybe 4 might start with the compressor, and then the hotter the day, the head pressure goes up more and more. On hotter days, you bring on more and more condenser fans with pressure switches to maintain a nice constant head pressure on the high side of your system. Now, water-cooled systems are a little more efficient than air-cooled systems. They're more expensive to install. They're more expensive to maintain. They're a little better on energy. These are generally going to have a cooling tower where water trickles down and evaporates, and through that evaporation process primarily we get rid of the heat of the building. And the water-cooled condensers can be very small, and you might have many of them. There are certain high-rise buildings, condominiums, luxury condominium buildings, where each tenant maybe pays for their own electricity and has a unit in the attic, and there's a little water-cooled condenser there with it, and then they pump the water that has picked up the heat to the cooling tower, and it trickles down, evaporates, gets cooled off, and gets pumped back down. So you might have 300 or 400 of these little packaged air conditioning systems with a water-cooled condenser, all being served by one giant cooling tower. Or you might just have a centrifugal chiller that has 2,000-3,000 tons, where you have this condenser water, and we use water to cool the condenser, which is typical, and then we put it through a cooling tower, and that cooling tower serves that centrifugal, or maybe 2 giant centrifugals. So water-cooled is a big part of commercial and industrial equipment, and there's a whole, I do whole lectures on that. You can look for that in my other classes. And again, with any system, anti-short cycling, that's actually gotten more and more and more pervasive over the years. And one of my, which I should create my 10 commandments, is once a air conditioning or refrigeration compressor shuts off, don't ever restart it for any reason for 2 or 3 minutes. You trip over a cord, you unplug something, don't plug it right back in. Let the pressures equalize as much as possible. Let that compressor cool off. And more we have this concept all throughout the industry where we're not going to let things stop real quick. That kind of can ruin things. We're going to let them sit off for a little bit. And even just off topic a little bit, new thermostats in refrigeration, little tiny boxes, commercial boxes, actually will have that built into it, where when the thermostat opens for, let's say, a little reaching cooler, it's not going to let it close again for a couple of minutes, just to make sure that we don't overload the compressor. Okay, again, a commercial condensing unit. The condensing unit means that the compressor and the condenser are together in one box. And again, in commercial applications, bigger equipment, you always have like compressors that have their own contactor. Each condenser fan, or maybe 2 condenser fans, might share a contactor. But you're not going to be finding on larger equipment where compressors and condenser fans share this one little 30 or 40 amp contactor. It doesn't happen because the loads are big enough where they all get their own. Okay. Now, this diagram is probably too hard for you to see. We're going to get off of it, also due to time constraints. And then here again is package units on the roofs. There's an older model. Again, these get dirty and they should be cleaned at least once a year. Best time to do that would be right before the first heat wave of the year, in spring actually. Again, this equipment is on the roof. It's all there. It has a disconnect. There's a blower section. A lot of times there's a belt with these fans on these package units. Again, you may have one or two compressors inside the package unit. All right. Some older systems will actually have a hot deck and a cold deck. And again, we have a compressor section, a blower section, and then maybe where hot air comes out or cold air, and then we have dampers that can dampen that down. Sometimes we'll have a remote condenser. A remote condenser means that the condenser all by itself, this lonely condenser, no compressor, it's not part of a condensing unit, and we're getting rid of the heat somewhere where we don't care about it. I wouldn't say this is really common, but those systems are out there, so you should be aware of remote condensers. I think on a percentage basis, from my experience, it's more common in refrigeration. Okay, and here's a look at, again, a split system. Again, the system's split in half. We have the condensing unit that sits outside the structure. Here, what's going to be in here? Compressor and a condenser. Over here, you've got the air coming in and the air coming out, the cold air coming out. In here, this would be your evaporator, your blower section, and your metering device. Okay, and then again, your condenser fan would be here with the condenser. The two pipes going back and forth would be your liquid line and your suction line, the bigger one being the suction line. Again, we talked about water-cooled package units where they can be much smaller than what you think, let's say, a 5-ton package unit would be, because you don't need to have all this extra space because they're more efficient and the water takes the heat away, and then you have a separate cooling tower that actually evaporates the water and gets rid of the heat. So you will need to have a condenser water pump that serves these water-cooled package units. Okay. With any system, there's really a control loop. And let's take a little look at a diagram with that to understand it better, just this concept of what a control loop is. Let's look at the basic control loop here. Here you have something like a sensor or a room thermostat. It senses, hey, the room is too warm. Let's close our contacts and energize a contactor. The contactor closes its contacts, brings on the compressor. The compressor runs. The building gets colder. The thermostat senses, hey, it's cold enough. We don't want to make it any colder. It senses that. It opens its contact, shutting off the contactor, de-energizing the compressor. This is the idea of an automatic control loop. And we have many different ones, more complicated in commercial industrial applications, but we're going to look at some of these things that are part of that now. Older systems, pneumatic controls. I don't think there's been any brand new buildings from the dirt up that have been built since the early 1990s that have used pneumatic controls, but there are still hundreds of thousands of buildings that have pneumatics in them in North America. Okay, and so it's important to still understand them, because a lot of times you have to work on these systems, and this is using air instead of electricity as a signal to control equipment. So you're going to have an air compressor somewhere like you would at the gas station, builds up the pressure, sends it out, and then you have these pneumatic thermostats that can vary the pressure. The main air comes into the thermostat, and then depending on whether it's direct acting or reverse acting, that's another lecture, it's going to send a branch signal out to a valve or a damper to provide cooling and heating. Originally, this was a way to provide proportional control. I mean, think of the 1920s. Oh my God, and 30s and 40s and 50s and 60s and 70s. Wow, you don't just have on and off, but you can open a damper a little bit more or a little bit less, or a hot water or chilled water valve a little bit more or a little bit less by varying the air pressure. Also, as the country grew and high-rises were built, Grandpa helped build the Empire State Building, people worried about fires. And electricity, back then, plastic, no. Cloth wires. So, fires, high-rises, let's use pneumatics, right? So there's a lot of benefits to pneumatics, and I still like them a lot because I think they're a lot less expensive and reliable than some of these digital motors that we use for dampers and valves. But we're going to all digital now, and hopefully over the years they'll come down in prices more and be a little bit more reliable and last more years than what I've seen them lasting. So here we have pneumatic system. This is just a simple hot water reheat system where you're getting your main cool air if you need it, and then if you don't, you're just providing air, and then you have a hot water coil pretty much near the occupied space, and it's a small coil. Because again, remember, you don't need as much hot water coil as you do chilled water coil for the same space, let's say here on the West Coast, because again, this might be 190 degrees, right? So this might be 130 degrees warmer than the room you're trying to cool. However, when you have chilled water, we're only getting 45 degrees, so that might only be 30 or 40 degrees cooler than what you're trying to cool. So you can see that you need a very little hot water coil, and that's why we can have a coil here near the zone, which is called hot water reheat. And here's the hot water valve being controlled by a branch pneumatic signal. Okay, now this is a more modern system. We're using direct digital controls. The two main signals that we communicate with is 0 to 10 volts DC or 0 to 20 milliamps. And this is a modern system here where you always have to have a certain amount in commercial industrial, like at least 15% fresh air coming into the building at all times. Or sometimes 100% cool air called Economizer Mode, where when you have a bit of a load inside, it's 75, it's 76, 77 inside, but maybe it's only 60 degrees outside. You want to provide some cooling early in the morning. You can open up these dampers and flush the building with cool outside air, not having to run your expensive chillers. So here you've got your outside air, and this symbol here, this is actually an official ASHRAE symbol on a blueprint for an air filter, and that's what this is. This is your air filter. Here's your return air coming back from the space, from the building, and then we can either exhaust some outside or bring it back. That, let's say you're in a minimal outside air situation, 85% return air, 15% outside air. This is called mixed air right before the air filter. And then we go through, this is by far more common than your double duct systems nowadays, this system here. The hot water coil, the chilled water coil. I prefer it when they're flipped, where the chilled water coil is here. So that you could, because with the chilled water coil, you're always having a condensate pan. So after 10 years, you may need to remove the filter and clean this coil. You can use water, and the condensate pan can take the water away. Hot water coil, no condensate pan. And then the air, the blower is going to blow that air down into the space. You've got a supply air temperature saying, hey, it's 55 degrees air we're providing. And so these are your dampers again. Let's move on to the next slide. Again, they're kind of going back, for some reason on this slide here, to a pneumatic system. Again, this is your main air coming in, and then this is your branch air, usually going up into an attic. And this is really just a booster. Sometimes with small systems, you don't even need this controller. And the reason it's there is because this is a bigger diameter, a 3/8 inch line that provides more air pressure, well, greater total pressure, more flow, and this acts as a signal, this quarter-inch signal, and allows it to go to your hot water valve and your chilled water valve. This is your chilled water coil. This is your hot water coil. This is the air handler fan. And you provide either hot water when you need heating or chilled water when you need cooling, and you can get a little bit more or a little bit less of whatever you want by these valves opening and closing a little bit more or a little bit less. So again, here's a pneumatic system that is controlling these valves by pressure on the diaphragms. Again, with direct digital control, it's commonly stated as DDC. We use a microprocessor for that. I really think in the future we're going to get to the point where we have something that looks like an iPhone just stuck to the wall, wireless. You'll have an app on your phone. You'll be able to communicate with any building, any sensor, without having all these buildings hardwired, which takes a lot of time and money to do that and integrate it into systems. And I think we're almost there yet, but not quite. Really, I had a meeting with Johnson Controls here at the beginning of 2020, and they were just starting to look into it. Okay. All right, let's take a look at this digital controller here. Let's look, these two are identical. Let's look at the one with the color. And you might want to plus this up when you look at it. The inputs to the digital controller, the information we're getting in, supply air. How cold or warm is the air going out of the system that we're giving the people? What's the air temperature coming back? What's the outside air? What's the mixed air temperature? What's that temperature right before we go in the air filter? Okay, and then this is dealing with humidity. And then what are the outputs? What are some of the things that we can control with this information? So then there's a program here that the circuit board has in it that will make decisions. Like, let's speed up the fan. We need more CFM. We need more air. We're getting a reading here that the return air is high, the outside air is low. We're not going to run the chiller. We're going to open the outside air damper and run the Economizer mode. We also can control our heating valves and dampers and our cooling valves and dampers. So you can see these inputs and then outputs, and you can have giant systems. I used to work on a facility with 18 major buildings and 500 chilled water coils and 500 hot water coils for each of these zones. And you could sit at one computer and look at all these things and change the rate of airflow and the temperature and the schedules. And this is all part of modern energy management for commercial systems. And again, on residential, again, because of economy of scale, we don't really have that. We're not having all this elaborate stuff because, you know, you buy one outside air temperature sensor and have it inputted into a computer, which takes care of 500 or 1,000 rooms. The cost is going to be kind of the same for one person's house. So you can see what I mean by economy of scale. And again, usually there's just a regular computer, or we may be able to access things on our phone now to get alarms or turn things on or off. And that concludes my lecture on commercial and industrial air conditioning.